GATE 2019 Civil Engineering Set 1 Question 34. Sedimentation basin in a water treatment plant is designed for a flow rate of 0.2 meter cube per second. The basin is rectangular with a length of 32 meter, width of 8 meter and depth of 4 meter. Assume that the settling velocity of these particles is governed by the Stokes law. The density of the particles is 2.5 gram per centimeter cube. Density of water is 1 gram per centimeter cube. Dynamic viscosity of water is given as 0.01 in CGS units. Gravitational acceleration is 980. And if the incoming water contains particles of diameter 25 micrometers, which are spherical and uniform, the removal efficiency of these particles is. 4 options are given: 51%, 65%, 78% and 100%. The relevant NPTEL reference has been listed. When we talk about the sedimentation efficiency of a tank, we consider a particle that has been introduced at the top of this tank and it settles at the bottommost point, as this is the most probable point for the particle to get settled such that all particles are removed. If it settles before this point, it is well and good, but even if it settles at the last most point that is possible for settling, it would still be considered a good enough settling. So for this, we calculate the surface overflow rate, that is also abbreviated as SOR. So this is found by comparing the height of the tank or the depth of the tank with the settling time, that is TS. So this settling time should essentially be same as the volume of the tank divided by discharge. This can be found as we will process V volume of water at the rate of Q in TS time. So TS will be V by Q. This can be written as HQ over V, and V is nothing but the volume of the tank. Since it is a cuboidal tank, we can assume it to be length into width into depth. This would give surface overflow rate as Q by B. It is called as V naught. So this is the settling rate of a particle to settle with 100% efficiency. So if the settling rate of a particular particle is greater than this value, it will settle with 100% efficiency, that is all particles of that kind will get removed. But if the settling rate of the particles is less than this value, the efficiency will be as a fraction of this V naught. This Vs is given by Stokes law, that is nothing but GD square by 18 times of the kinematic viscosity into specific gravity of the particle minus 1. Here d is the diameter of the particle. So using Stokes law, we can find the settling rate of a particle or the settling speed of a particle, and then we can compare this Vs value with the V naught computed here, that is the standard value for 100% efficiency. Once we have taken the ratio, we can find the efficiency of settling of a particle. In case Vs is greater than V naught or equal to V naught, it will always settle with 100% efficiency. But if it is less, we should use the second equation here to compute the efficiency of settling. The given data in the question is, here we can see that few of the parameters have been given in meters, but few of the parameters are in centimeter units. So we should take care of that while using the corresponding equations. So firstly, we will try to compute the surface overflow rate, that is V naught, which is given as the flow by the area of the tank. Here the flow is 0.2 meter cube per second and the area will be 32 times of 8. This would give V naught as 7.8125 into 10 to the power minus 4 meter per second. Secondly, we need to find the settling rate of the particular particle whose diameter is given as 25 micrometers. So the settling rate is governed by Stokes law for a spherical and uniform particle, that is GD square by 18 gamma into GS minus 1. Here the specific gravity of the particle will be the density of the particle by the density of fluid, that will be 2.5 in this case. So here what we can do is we can substitute all these values in CGS units, and finally that would give us the settling rate in centimeters per second, and then we can directly convert it to meters per second. This reduces the hassle of converting all the units here one by one. So we can substitute everything in CGS units, get the answer in CGS units, and then finally convert it to meters per second, and then we can compare this Vs with V0. So G is given as 980, D can be taken as 25 times of 10 to the power minus 4. Since we need to consider this in centimeters, specific gravity is 2.5 minus 1 divided by 18 times of kinematic viscosity is nothing but dynamic viscosity by density, which will be 0.01 divided by the density of water, that is 1. So 0.01 by 1. This would give the value as 0.051 centimeters per second. This can be now converted to meters per second. That would give 0.3051 meters per second. Now for finding the efficiency, we need to compare Vs with V0. This would give us the efficiency of settling. So Vs is 0.3051 divided by 7.8125 into 10 to the power minus 4 into 100. The efficiency will come out to be around 65.33%. So a sedimentation basin was given whose flow rate was known, the dimensions of the tank were given, and it was told that the particle settling is governed by Stokes' law. The diameter of the incoming particles were given, and the removal efficiency or the settling efficiency for these particles was found out to be around 65%. That is option B. The relevant NPTEL reference has been listed.